Hello students, future doctors and engineers. Welcome to our YouTube channel MedG Exam, the platform where smart work is always preferred over hard work. I am Pawan Shah with cream of the theme series in physics, starting with class 12. We are doing chapter 1, electric charges and field. Today we will discuss part 5 of that. Topic included will be electric field intensity at any point of an electric dipole, torque experienced by an electric dipole in a uniform electric field lines and their properties, electric field lines for some charge configurations. Okay. Let us do first electric field intensity at any point of an electric dipole. As shown in this diagram, we have made a dipole plus q minus q, and it has some separation, and the dipole axis is, or dipole moment is p vector, that is shown by a red line. Okay. If we resolve and O is the center point of this dipole, and we want to find let electric field intensity due to this dipole at point Z. Let this point is at Z. Here we want to find electric field intensity due to this dipole. If we resolve this p vector into two components, one along this ZO line, then it will be p parallel equals to p cos theta, and one perpendicular to this ZO line, that will be p perpendicular, that is p sin theta. Now we know that this ZO will be, Z point on ZO will be parallel to this p cos theta, p parallel equals to p cos theta. So this will be the axial position. The Z point Z will be at axial position of an electric dipole, and for that we know the formula for axial position. If this distance is x, ZO distance is x, and this ZO line makes angle theta with the dipole moment, then at axial position Z we want to find electric field that we have derived already. The formula will be 2 kp cos theta upon x cube, because p is here p cos theta, because it is parallel, p parallel. For that we have written p cos theta. So E equals to 2 kp cos theta upon x cube. Okay, and this p perpendicular is the component of perpendicular component to dipole moment, and this line ZO line is perpendicular to this p perpendicular, So the dipole moment due to this will be the equatorial position for this p perpendicular. This ZO will be the Z point will be at equatorial position. So at equatorial position, dipole moment will be kp sin theta upon x cube. And these two are the two components at point Z. We will find resultant of these two electric field intensity, that will give the net electric field intensity at point Z due to this electric dipole plus q and minus q. And let this alpha is the angle made by the resultant with this ZO line. So we will also find the relation between this alpha and this theta. Okay. So first let us find the resultant of these two electric field lines at point Z. That resultant E can be written as 2 kp cos theta by x cube whole square plus kp cos theta by x cube whole square and under root of this. That will be equals to, if take kp by x cube as common, then inside the under root there will be 2 cos theta whole square of this plus, okay, this will be sin theta, not cos theta, this will be sin theta, sin square theta, kp by x cube. So this will be 4 cos square theta plus sin square theta. That can be written as kp by x cube under root 3 cos square theta plus cos square theta plus sin square theta. This cos square theta plus sin square theta will be 1. So finally we can find the magnitude, and that magnitude will be, we have formula for magnitude, kp by x cube under root 3 cos square theta plus 1. So this will be the formula. Okay. Now if you find the relation between alpha and theta, from the diagram we can write tan alpha will be kp sin theta by x cube upon 2 kp cos theta by x cube. That we can write tan alpha equals to kp sin theta by x cube into x cube by 2 kp cos theta. In this x square, this x cube and this x cube will be cancelled. Kp and kp will also be cancelled. So we can write here tan alpha will be equals to sin theta by 2 cos theta. That means tan alpha will be equals to tan theta by 2. That we can write alpha equals to theta by 2. So this is the relation between alpha and theta. Now there is another expression that we have to find: torque experienced by an electric dipole in a uniform electric field. So here we have drawn this uniform electric field lines, and this is the electric field uniform. We have placed dipole minus q plus q distance 2a, dipole length 2a in this, and in such a way that this dipole moment p vector makes angle theta with the electric field. Okay, if we draw perpendicular from plus q to this, from this plus q, that distance will be 2a sin theta. Okay, now if we want to find torque, we know the formula for torque, that is force into perpendicular distance, force into perpendicular distance. So torque will be equals to, force is one of the force, pair of force, out of pair of force we will take one of the force, QE into perpendicular distance is 2a sin theta. That we can rearrange as E 2aq sin theta. That we can write as PE sin theta. Finally, that can be written from the vector, it will be P cross A. So this is the expression for torque when a dipole is placed in uniform external electric field having dipole moment P. Okay, let us see a few properties related to electric field lines and the definition of electric field lines. See, when we move a positive charge particle, unit positive charge particle in the external electric field, it will follow a path. Okay, if we draw a line along that path, then that line is said to be electric field lines. The line drawn along the path traveled by the positive charge particle in external electric field is said to be electric field lines. So electric field lines are imaginary lines drawn along the path when unit positive charge is free to move in the external electric field. Okay, electric field lines have some properties. Definitely electric field lines are imaginary, we have discussed that, and it is continuous. There is no breakage of electric field lines. Okay, and electric field lines do not form closed loop. The reason is that why electric field lines do not form closed loop, because electric field intensity or electrostatic field intensity is conservative in nature. Conservative in nature. Due to that, it will not form closed loop. Okay. Now the next point is that, fourth point, tangent at any point will give direction of net electric field at that point. Means that this is electric field lines and we want to find direction at this point. Then at this point we will draw the tangent. The tangent drawn at this point will give the direction of net electric field at that point. At this point is A. At this point the direction of electric field line will be A. Let another point is B here, and we want to find direction of electric field, net electric field at this point. Then again we will draw here tangent. That tangent will give the direction of net electric field intensity at that point. So that is the fourth point. And the next one is, electric field lines do not intersect. Two or more than two electric field lines will not intersect. Let this is one electric field line and this is another electric field line. And let it intersect here at this point. Let it is point X. At this point it intersect. Then at intersect, according to that, we will draw a tangent. Tangent for this will be along this, and tangent for this will be along this. So there will be two different tangent at the same point. That means two different direction of net electric field at the same point, which is not possible. Due to that reason, two or more than two electric field lines do not intersect each other and do not form closed loop, that we have discussed already in point number 3. The seventh is the relative crowdness will give strength of electric field. That means, let us draw here, this is electric field lines. This is electric field lines drawn. This is electric field lines. So here there is more crowd, but here less crowd. More crowd, the region where there is more crowd of electric field lines, at that region the strength of electric field will be more compared to the region where there is less crowd. That is the meaning of point number 7. And one point also we can write, that is very important point we have missed here, and that is electric field lines starts from positive charge, and ends at negative charge, That is an important property. So all these are properties related to the electric field lines. Okay. Now let us see a few configurations drawn for electric field lines. First, for positive point charge, if this is plus Q, for plus Q, as we see in the properties, the electric field lines will start from positive charge and ends at negative charge. So this will be gone in all directions uniformly for positive point charge. Similarly, for positive negative point charge minus Q, the lines will be same, but arrow will be opposite to that of positive point charge. In case of negative point charge, arrow will be opposite, that we have drawn here. Okay. Now for a pair of positive charge separated by some distance, so let us take this is a point charge plus Q, and this is another point charge plus Q. This is the pair of point charge. For that we have to draw the electric field lines. We know that electric field lines starts from positive and ends at negative, so it will go like that at infinity. In this way, this will also go like that in this direction. Another we can draw in this way, it will go like that, it will go like that. Here also it will go like that, it will go like that. Again we can draw so many lines symmetrical to it. So these are the electric field lines, not exactly drawn, but yes, more or less we can draw. This way we can draw the electric field lines. This would be uniformly, but I have tried to draw. Okay. Similarly, for negative point charge, if here is a negative point charge minus Q, and here is also a negative point charge minus Q, for that we can draw. It will be similar to this one. It will be similar to this one, but the only thing is that the arrow will be different in this case. So in this case, it will be like that. Electric field lines will come from positive to negative. It will be like that. In that way we can draw. Like that. Okay. The last one for an electric dipole, that is already drawn. This is the plus Q charge, this is the minus Q charge, and so all the electric field lines will go away from the positive charge towards the negative charge, and at negative charge all the electric field lines will come from positive to negative, and that here it has drawn already. So students, if you want to download the PDF, link has been given in the description box. And if you like the video, please like, share and subscribe.